Thank you very much. This is a little lecture now on space resources and what to actually expect out there. I am Valentin Troll. I am a professor for petrology. That's the science of rocks. And I'm here in the natural resources discipline section of the geoscience department. So I specialize in rocks and ore deposits. And so today I will summarize a little bit on what to expect out there. And I will focus mainly on metals. There's some other things like helium on the moon that might be attractive, but I won't really touch on that. My focus is today what to expect out there in terms of metals, because this is also economically very important for us. So meteorites and space resources with a focus on metals. So the Earth, of course, and we all know that, just to ease us in, is a unit within the solar system, and the solar system consists of the sun, the planets, their satellites, and of course the asteroids, and then we have comets, and we have meteorites. Comets and meteorites are more irregular, and meteorites are obviously the things that have fallen on other planets or on other heavenly bodies. The sun itself is one star within our galaxy, and the galaxy is, it's a large kind of feature, and it's lens-like in form, and it's got a diameter of about 70,000 light years. Beyond our own galaxy, there's a large number of other galaxies, and I just want to mention this. These extragalactic nebulae are scattered fairly uniformly throughout space, we believe. The nearest to us is the Andromeda Nebula, but I won't really touch on that because let's be realistic. In respect to space resources, what's important is the things that are reasonably close to us. So we need to focus on Earth near objects and maybe as far as the asteroid belt, but these other things, they are far beyond our reach for quite some time. So I won't really talk much about them. So the focus, as I said, is the solar system, and people have, of course, seen meteorites fall for quite a long time. There's old records going back to the Roman Empire, to the Egyptians, etc. But real kind of scientific recording only started at around about 1800. And then scientists became finally convinced that there's actually stones, rocks falling from the sky. And that was when we realized there is these heavenly objects that are out there, and they're not completely out of reach. And our technological development over the last decades has, of course, given us hope that within a few more decades, we might be able to interact with these heavenly bodies in a much closer way than we used to in the Earth history so far. So we know that these objects can be reached ultimately, and we know that some of them have fallen on Earth. So we have an idea what they're made of. And for this reason, we can speculate about the future and whether we will be able to get out there and retrieve some of the material. And here's a very schematic artist's impression of the solar system, the rare situation that everything might be lined up. And what we see there is the inner planets and the outer planets, the larger gas giants and the inner terrestrial planets. And there's a bit of a gap in between. I'll talk more about that. And that's where the asteroid belt is located. And the little inset in the lower right gives us a sense of that. There is a belt made of many small objects, and that is likely a good source for metals. And I will focus very strongly on that part. But let's quickly explore the reasons. And Michael Höök was talking about the situation on Earth with our supply of resources, particularly metal resources. And this is where we are running into a little bit of a dilemma increasingly. So we are, of course, very keen to do things that are good for the environment. We have climate problems that we need to tackle. And we hope that by going off fossil fuels, we can actually do something about the climate. And for that, electric vehicles is a big topic right now. But the problem with electric vehicles is that they will require a lot more metals. And if we really want to electrify the traffic, and also thinking about alternative energies like wind and solar, a lot more mining will be needed. In fact, more mining than we've ever done before in human history. So here's just a little kind of sketch. It's a US source, so this is given in pounds, and this is about copper. Copper is a fairly common metal, and the amount of copper that is required in electric vehicles is a lot more than in conventional vehicles. So a lot more copper would need to be produced. And here I picked something up from social media. This is a BBC article and a comment on it, and here's some numbers. You can find them also in real papers out there. Some of them are already on Studium if you're interested. But just to kind of switch Britain's petrol fleet of vehicles to battery electric fleet, the amount of cobalt, the amount of lithium, the amount of neodymium and dysprosium, that's two rare earth elements, is just staggering. And I don't think people have a good idea about this. And cobalt is one of the crucial elements at the moment. We have real issues with cobalt. 65% of cobalt comes from Central Africa, from the Congo, the Republic of the Congo. And conditions there are not always ideal. And this puts us into quite some dilemma. So here is just a little bit of a projection. And by 2030, there's a reality that we need to face, and that is that even with going to places like Congo, even with trying to exploit the sources we have on Earth, we're likely going to face a supply and demand problem. If we're really going to push ahead with battery vehicles, lithium cobalt is the best type of battery we can do right now. Maybe there will be a change in technology. I'm a geologist, so this is not for me to develop, but if this is the way to go, then the demand for cobalt will be huge, and we will have real problems producing enough. And this is, of course, compounded by these issues with environmental conditions. And in Europe and North America, the mining industry is trying to be environmentally compatible and be at least as clean as possible. I've been up in Kiruna, and they're trying to be as sustainable as they possibly can. But this is not, of course, true throughout the planet. In many countries, the regulations are not quite as strict, and there is little control over things. So mining practices lead to pollution, and also remediation is not always a given factor. So here's some various images. The upper ones are from Africa, and their large areas are actually contaminated, and environmental pollution is in places quite rampant. So this is another problem we are facing. And of course, this leads to quite some opposition. And in many areas, quite rightly, opposition is in place because the working conditions that we're trying to improve here in Europe, they're not always maintained or adhered to in other parts of the world. Child labor in Congo seems to be a real problem. And you can read this up in various articles. This has huge health effects on the children involved. And this is, of course, a very grim situation. And if you drive electric vehicles, there is cobalt from Congo in your car. It's almost unavoidable. So we have these issues that are very hard to avoid. And this is not just specific to Congo. This is in many other parts of the world. The situation is getting better, but many countries don't have the controls in place to really kind of avoid these issues completely. Therefore, mining is facing often a very strong opposition in many parts of the world. And this is at odds with the demands for clean energy, for green energy, for green tech, which requires us to mine more. At the same time, mining is increasingly unpopular. So there is these counter streamings in society that are very hard to reconcile. And this, of course, yields us or kind of requires us to think outside the box. Is there any other alternatives where we can get metals from? And There's one environment here on the planet that we haven't fully exploited and explored, in fact, and that's the deep sea. So at the moment, there's a lot of efforts about deep sea mining, and the government of the Netherlands has just funded a huge project exploiting the possibility of harvesting material from the deep sea. But of course, there's new problems with that. The very deep sea is not very well explored. There's a lot of biodiversity that we don't really understand, that we haven't even recognized. And we are meddling with our environment if we go there. There's various concepts of how to exploit the deep sea. Chance is we wouldn't really go there as a human being, as a miner. We would actually have robots down there that would, like a Hoover, suck off manganese nodules from the ocean floor. But by doing that, they would, of course, disturb large stretches of the ocean floor as well. And the living creatures there would, of course, be affected. And deep sea mining, therefore, comes with this new dilemma that by trying to be environmental friendly on the continents, we are destroying the habitat of creatures potentially on the ocean floor. And this, of course, puts us into a really delicate dilemma. So how do we get resources for a growing kind of economy, for a growing world, for a growing population of our planet without making the environment suffer? And when I quickly remind us of the Sustainable Development Goals, I mean, we want to have a world with no poverty. We want to have no hunger for people. We want to have decent work and economic growth for everybody, and affordable and clean energy. We want to have industry and innovation and sensible infrastructure. I would just point out that there is quite some areas, large areas in Central Africa, for example, where less than 10% of the population have access to permanent electricity. So there's huge amounts of populations that still need to be lifted out of the current economic state. And just to achieve that, a lot of infrastructural development, a lot of economic development is needed. And for that, we would need metals. So this puts us into this kind of situation where we have to think, is there a possibility for getting metals from beyond our planet? And the ethics of this we'll discuss later in the course, but I guess today my task is to really explore, is there actually something that we would possibly want? And what would that do? And how much of it could be there? So let's explore this, but first a few definitions. We need to think about a few kind of names. Most of you know these, of course, but a meteorite is an object that falls from the heavens onto our planet. It comes through the atmosphere. And once it travels through the atmosphere, we call it a meteor. Once it lands, it's a meteorite. And smaller fragments outside the atmosphere are meteoroids. And once they're out there in the asteroid belt, then they're asteroids. So an asteroid can become a meteoroid, a meteor and a meteorite, but it's harder to do it the other way around. Going backwards is not so easy, but going forward from the asteroid to become a meteorite, that's a very common thing, we believe. So there's a lot of small objects out there in the solar system. Of course, there's planets and there's satellites like the moon, but the moon is effectively a lump of basalt. It's very similar in composition to basaltic rock on the Earth. It's a bit more rare earth enriched, it's a bit more titanium enriched, but it's not of ore grade. So while we could make a station there and while we could use some elements from the moon, I think the real thing we're after is the metals, and they are actually in some of the small objects. So the asteroids, small rocky objects, mostly between Mars and Jupiter, and they are often too small to see, but they are the ones we're really after. There is also the Kuiper belt objects, but they are very far out there. So I'll mention them, but they are probably too far for us. And here's a little sketch of the sun on the very left and the terrestrial planets following on from the sun. And then we have the asteroid belt marked in red here. And then the Kuiper belt is on the far right-hand side here beyond Neptune. And there's another belt of asteroid type bodies. But as I said, they are far away. So the asteroid belt is probably our immediate target beyond, of course, the moon. And this is where we would find asteroids that are made of metal. And we'll explore this a little further now. So what is going on there? Well, I mentioned it earlier. This is Bode's system. Mr. Bode, he worked out that there is a systematic distance between the objects in our solar system, and he identified that there's a vacant spot. And this is where the asteroid belt is located. So the inference is that there was potentially a planet that wanted to form, but it never quite made it, or several tried to form and they collided. We'll talk a little bit more about this in a few minutes. Nobody really has all the answers, but there is a field of debris out there, many, many small objects, and that is what is of interest to us. So here's a few more impressions, and there is various sizes of them. Some of them are several hundreds of kilometers across. Others are really small, and they are in this belt, the asteroid belt. And this is just before the large planets start in the solar system. And it's reachable. The Japanese have actually reached an asteroid, and therefore, technically, it can, in the future, certainly be done, I would think. So it's not completely out of our reach. So what is going on out there in the asteroid belt? Well, many of them happen to be rubble piles, we believe. And here is an image of an example. And this, as you can see, is made of many small objects. So this is a pile of rubble. It looks almost as if there's two larger lumps that have come together, and then they have a coat of rubble. Whether they are rubbly inside as well, we don't know, because they actually attract these smaller objects, and many people believe that there's a solid core and the rubble is only at the surface. So as I said, the Japanese were managing to kind of go close and even sample some of the asteroid material from one of them. And this kind of gives us a good idea that technically it's possible, but it's not always easy to work out what they are exactly, because this rubble material at the surface might cover a very different core. And if we do spectroscopic analysis, we might get a little fooled because of this surface cover. So there is a risk that we might be approaching the wrong one if we're not very careful here. So here's a few more examples of various asteroids. And as I said, there are various sizes. Some of them are hundreds of kilometers. And depending on how we technologically advance and how we approach this, it might be advantageous to go for larger ones or for smaller ones, depending on what we can actually do technologically. So the largest ones are listed here, and some of them were discovered already kind of hundreds of years ago. And there are several hundreds kilometers in diameter. And so many of them are actually of carbonaceous chondrite or of chondrite material. And we'll talk about this a little more when we discuss the meteorites, but some of them are of metal type. So here, for example, Psyche is of metal type, and it's about 260 kilometers across in diameter. So there's a lump of metal floating out there, several hundred kilometers big, and this is super attractive from an economic point of view. So how did these small objects come about? Well, I mean, given this amount of rubble out there, many of them collide. So, and that means that this is a bit dangerous out there. And if there was larger objects, the collisions would have kind of ground them down, and there's still ongoing collisions out there. So the sizes may vary therefore. So here's some kind of images from the various space probes, and here's some of the larger ones, Ceres, Vesta, Pallas, etc. And some of them are believed to have undergone almost no change since the beginning of the solar system. Others are believed to be fragments of planetesimals or small planets that got destroyed. So we have these different types out there, and we can use spectroscopy and, importantly, meteorites to explore this a little more. So here's another example, asteroid Ida, and Ida is about 50 kilometers long, and it's basically a rock floating around out there. And here we have different views of this. There's cratering, of course, going on, and Gavin will talk more about impact features and impact craters later on today. And this asteroid Ida, it actually has a little moon. You can just about see it here. There's a little moon. It's got its own little system of a satellite here and a major body. And here, this is kind of just about large enough to actually land on it if the gravity can be fixed, if these technical solutions can be provided, then this is the kind of thing we could potentially exploit. So based on emission spectroscopy, there is these different types. There is the C types. They are kind of carbon silica rich, and they make up the majority of the asteroids. There is the silicate types. They are about 17% of the asteroids. And there is a not so common type. It's the M type, the metal type. And that's the ones we would be really, really interested. So, and asteroids experience different stages of planetary differentiation. The primitive ones have likely not been part of making any small planets, while the more differentiated ones, they have been part of planets that got destroyed. So there can be remnants of shattered planetesimals of small planets. And that's what we actually want. We want metal concentrations, and they are, of course, in little cores of little planets. And this is what we're after. So, and because some of these were broken up, there's fragments of these, there's fragments of former cores floating around, and that's what we want to catch if we go ahead with this concept. So metal compositions and value, I mean, there is some estimates out there. They change all the time because metal prices kind of change. Some of these metal type asteroids, they have a lot of iron, but they also have nickel, cobalt, quite high cobalt concentrations, and of course, platinum group elements, and that's super kind of valuable. So, and because of the metal prices rising for many of them, iron is not kind of getting more expensive, but nickel and platinum group elements, they are very expensive. Cobalt is also very high in value. Then some of these asteroids are rising in value by terrestrial economic terms. Here's some comparison from 1994 to 2012. And you see that the numbers are staggering. NASA has estimated that some of the larger asteroids could be the value of 70,000 times the entire world's economy. So if we take all the resources on our planet to go there and harvest them, we will still make a profit. That's the logic of it. And this is why people like Elon Musk are, of course, very keen to exploit this possibility. So the compositions of asteroids can, of course, be better studied from meteorites, and I will focus for the rest of the lecture on meteorites because these are materials we actually have in hand. We can directly study them. And most meteorites are fragments from the asteroid belt. There is, of course, some exceptions. We have also some meteorites from Mars and from the moon, but they are relatively kind of uncommon. And here we have three main types, and we have stony meteorites, Stony-Iron Meteorites, and the iron meteorites. And the iron meteorites is what we want for exploiting the metals. Stones are very much like terrestrial rocks, like stony terrestrial rocks. And the stony iron ones, they are mixtures between silicate materials and metals, while the iron meteorites, they are almost exclusively of metal. And they are, of course, the most attractive for us. So this last type here, this is what we are after. And these meteorites, they have become available in large numbers over recent years due to various sampling campaigns that NASA did in Antarctica, but also in various deserts like the Sahara. So we have large amounts of meteorites from Antarctica and from Northwest Africa. And it looks like that most of them are of asteroid belt origin. So meteorite matter is actually continually falling on Earth, and mostly as dust, but sometimes there's of course a bit of a larger fragment, and then we see that as a shooting star, for instance. And some of them can even be observed as faults, but of course, this is a more rare situation. Meteorites consist essentially of nickel-iron alloy, crystalline silicates, and this is very similar to terrestrial minerals, olivines, pyroxene, mixture of these. But there's virtually none that resemble traditional sedimentary or metamorphic rock type that we have on Earth. There can be some breccia types. They have been shattered, but not kind of fluvial deposited stream sediment types. Things like that have not been observed, of course. So meteorites have a fusion crust, and this is usually what happens when meteorites are traveling through the atmosphere. They melt, and therefore they often have this black crust, and this makes them very distinct. And this is good to see when you're in Antarctica or in the Sahara. Then you can pick them up quite easily. And this is a distinguishing feature. And here, I'm sure Gavin will say a few words about this, but here's a bit of statistics. I mean, we have a 1 meter sized object falling on Earth about every few weeks, 5 meter sized once a year. 1 kilometer size is a million-year event, and 100 million year frequency is for really large objects like what caused the Chicxulub impact. It's a very rare thing, and it's very unlikely that in your lifetime you will experience a thing like that. So here the fusion crust is important for identification. This is how we find them. And here's a few impressions. And therefore, when you go to Antarctica, NASA can pick them up in large amounts, and ice often pushes them together as well. And because they warm up in the sun, they melt themselves into little kind of holes, and maybe they get concentrated at times. And if you find one of these concentrations of meteorites, you get a large number of samples very swiftly. So, and of course, you can also kind of look in deserts. The fusion crust makes them stick out. And over 2,000 meteorites have been made, finds have been made over the last 2 decades, I think. So it's a large number of them that have become available for our study. Now, as I said, there's 3 fundamental types, and I want to keep it simple. I mean, of course, if you're a really heavy meteorite researcher, you will subdivide this a lot further. But we have the stony ones, the iron ones, and the stony iron. So effectively, stony ones are like rocks, the irons are fully metal, and then we have these mixtures between silicate rock types and iron or metal material. So when we look at the distribution, most of them is what we call ordinary chondrites. They are stony meteorites. The stones are subdivided into chondrites and achondrites. Chondrites are those meteorites that have little chondrules, little former droplets of material, and they are somewhat different to the other guys. All the other meteorites make only about less than a quarter of the meteorites. So the stony irons are quite rare. The achondrites are a little more abundant, and then iron meteorites are only a few percent actually. And that's also what we need to think about in terms of the asteroid belt. Most of the material in the asteroid belt actually will be ordinary chondrites. And while they have metal, what we really would want is an iron meteorite. So we have to be a little careful in picking the right one if we ever go out there to harvest them. So here's my little summary diagram. It's a little simpler. We have the chondrites. 85% of all the meteorites are chondrites. And then we have achondrites, that's stony ones without chondrules. Then we have irons, about 3.5%, and stony irons, usually about 1.5 to 2%. So I'll go through these different types now in a little bit more detail. So the stones, or sometimes also referred to as aerolites, can be subdivided into chondrites and achondrites. We said that. And the chondrites are so named because they have these little round bodies called chondrules. And they're on average about 1 millimeter in diameter, and they're often of classic silicate minerals, olivines, pyroxene, and they seem to be unique to these meteorites. And they have not been observed in terrestrial rocks, and that's of course making them significant in terms of explaining their origin. Average composition of the chondrites is about 40% olivine, 30% pyroxene, and up to 20% nickel iron metal. And that is attractive. So they are actually not completely useless. If we ever by accident happen to kind of land on one of them, they are useful, but of course the concentration is not as high in terms of metals as a pure metal one. And they can have some iron sulfide like Troilite FES up to about 6%, so this could be attractive as well. So here, a quick impression of these chondrules, these little probably former droplets of material, and they can be of various size, but on average about maybe a millimeter, but they can be up to a centimeter. And usually you need a microscope to see them. And the chondrites are the most common type. And here's an impression of a certain kind of meteorite that falls into that group. And as I said, the nickel iron is attractive. Usually they're also magnetic. So, and they have several percent of FES. So if you want, they have low grade ore quality compared to some terrestrial rocks. So the chondrite group is very common, and they have a subgroup, the carbonaceous chondrite, and they is about 5% of the chondritic meteorites, and they have organic compounds. So they have some hydrocarbon chains, and this, some people argue, could be the origin of life. Maybe this is how life was imported onto Earth by a meteorite of this type. I'm not entirely sure about that, and of course people have speculated about this, and this has led to all sorts of experiments. And they also have some what's known as calcium aluminium inclusions, CAIs, and many people believe this is the very oldest material we have in the solar system. And these organic compounds, as I said, they led to a lot of thinking work by many people, and it was shown by Mr. Miller already in the 1950s that you can produce these organic compounds in the carbonaceous chondrite by inorganic means. So it's not strictly necessary that life is involved here, but of course the possibility is there. So these carbonaceous chondrites, they often are very dark, and they contain these carbon compounds, and they are not strictly of interest in an economic sense, but this is a small percentage of these meteorites. The chondrites, they are on average very similar in composition to what we believe to be the starting material of the solar system. So here's a plot of the abundance of most elements, apart from the volatile ones, in the carbonaceous chondrites, and the abundance in the solar atmosphere. And we find that apart from some volatile elements, we have a really very good match. So this gives us the idea that these chondritic materials were the starting composition of the solar system. And this would imply that many of those chondrite materials in the asteroid belt were not part of major planetary formation processes, but are largely unmodified material that is still floating around in the asteroid belt. So these are likely some of the oldest solids that we have, and they are the building blocks of the solar system. And maybe there were some small bodies, but chances that they will not be part of major planets or planetesimals. And here's some more impressions of them. You can see the little round kind of dots everywhere. This is the chondrules, and this is how they would look like. And as I said, some of these stony kind of asteroids, they might actually contain sulfides as well. This could be attractive, but they are not the key interest. I think we really want to go a little bit further. I'm going to talk about the chondrites just for completeness sake, but also from a metal potential. They're also not the key thing. They are also stony. They are very much like magmatic or igneous lava or plutonic rocks on Earth. And there we find that they are economically no more attractive than most igneous rocks on our planet. And this group would also include the Martian and lunar meteorites. And here's a few examples. Here's a lunar meteorite, And here is various other achondrites, and you see they are a bit like terrestrial rocks. So they are not outstandingly of interest here. So they're a diverse group of meteorites. They do not contain chondrules, and they're usually much more coarsely crystalline than chondrites. They resemble terrestrial rocks in their texture and often also approximately in their composition. There is a small group of meteorites, the SNC meteorites, where we are pretty confident that they come from Mars. They tend to be younger. They tend to be somewhat different in composition, and some of the inclusions are very similar to the Martian atmosphere. So I just want to mention them for completeness sake, but they are not particularly important economically. So here we have another example, and if you're lucky, they could be like low-grade ore on Earth, but this is not kind of the material we would be focusing on too strongly. So another way to classify meteorites is into differentiated and undifferentiated ones. And the chondrites would be undifferentiated ones, while the ones I've just shown, they would be differentiated. They would have been part of a major planet formation process of some sort, and they would have experienced volcanic or magmatic processes. And therefore, we already can point out at this stage that we have a chemical divide between materials that are largely unmodified and materials that have been part of parent bodies, and they have experienced some differentiation. And this is what we kind of need for increasing the metal content of these materials. So I'd like to kind of talk about stony irons now, and this is a very rare group. And there we have more metal, and there's two main types, pallasites and mesosiderites. And the pallasites, they are believed to be part of a former planetary body, maybe the area between the core and the mantle, if we use the Earth as an analog. And then we have the mesosiderites. They are more Brexia type, and it's believed that maybe they are impact related. So here's some of these examples. You see large silicate minerals, but you also see metal, and particularly camosite and taenite. And this is nickel iron alloys of various nickel concentration. So here, the key types, as I said, pallasite and mesosiderites, they are of interest, and pallasites could be very attractive, and mesosiderites as well. Pallasites have a more continuous metal phase, and this might be easier to exploit. So, but they're very rare. And this is therefore very hard for us. If we have to pick some target asteroids, we would have to be sure that we're picking the right one. And I guess potentially pure metal ones might be more attractive. So here, the pallasites, just to summarize, were likely part of planets, but somewhere inside the planet, while the mesosiderites, they're more like impact breccias, and therefore they have formed in different parts of planetesimals or small planets. So the pallasites, they can have up to 11% nickel. They can have 6,000 ppm cobalt. So this is attractive. They have chromium. They can have copper. They have a bit more gold than the Earth upper crust. They have a bit more platinum group materials and some rare earths. So as I said, they're not, they're quite interesting in this context. So this is a potential kind of scenario for harvesting. But they're rare, as I said, and they would also be rare in the asteroid belt. The mesosiderites, they are similar in composition, but as I said, the texture is a little different. Here we might have up to 10% nickel, 1200 ppm cobalt, which is quite a lot more than the average Earth crust. Chromium is relatively high, and many of the more rare Earth elements are there as well. So here, these could be interesting target materials. Now, let's go to the real thing, and that's the iron meteorites. And that's, I think, what we really would want in the long run if we go this way. And the picture on the right is a find, an iron meteorite in Namibia, I think. And this is how we come to know a lot about iron meteorites, and they are effectively completely metal. And they have a lot of nickel and a lot of iron, of course. They also have some iron sulfides, troilite in particular, as inclusions. And they show these exsolution lamellae, the Widmanstätten figures. And this is these kind of cross-hatched lamellae here. This is believed to be a cooling feature inside a planetesimal or small planet. And these are believed to have been part of a core of such a small planet. And the exsolution is often used, the width of these lamellae is often used to say something about cooling times, but that's of less relevance for us today. The main minerals are there is camosite and taenite, and one is more nickel rich than the other. I don't think we need to go into extreme details, but the taenite is the more nickel rich one, and they exsolve when they cool, and that makes these Widmanstätten patterns. Depending on the nickel content, there's further subdivisions, but again, they're not of key relevance for us today. Here's a few examples with fusion crust and cut open and polished. And usually you have to use a little bit of acid to bring out the Widmanstätten figures. And on the right-hand side, there's a large troilite inclusion. That's the iron sulfide, the dark blob there. So here's a sample that Renault kindly photographed. This is from the Natural History Museum in Stockholm. This is a Russian iron meteorite that was donated by the Soviet Union to the King of Sweden back in the Cold War period. And they have larger fall swarms in Siberia. Their sizes and shapes suggest that they are cooled down slowly and that they were part of these larger planets. And this is what is attractive. We can actually get material from inside a planet because in the asteroid belt, we have a broken up planetary system. And not only iron, there's also nickel and cobalt. And nickel is always present. Cobalt can be also quite high. Nickel can be up to 20% or higher. Cobalt would be also on a level as high as the best cobalt ore on planet Earth. So this is why people like Elon Musk and Tesla are so interested, because cobalt is vital for batteries. And this is the richest cobalt material we know of, and it's floating around out there in the asteroid belt. So this is the famous Cape York meteorite. This is, if you watch the movie about Smilla, the lady that came from Greenland and was involved in this big meteorite that was found there. This is actually the meteorite that gave rise to this story. It was found in Cape York in Greenland already in 1894, and it's a large lump. The largest part of it is actually in Copenhagen. And here we have iron, nickel, cobalt, and we have these large troilite FeS concentrations, and cobalt is present at several % level. So when it comes to trace elements, there are several thousand ppm cobalt, hundreds of ppm of chromium, there's copper, of course, molybdenum, there's platinum group elements, and they are much, much richer than in most of the other meteorite types, and of course, a lot richer than in the upper Earth crust. So all rare metals are expected in the core of these rocky planets, and therefore, if we have these broken up materials in the asteroid belt, they are highly interesting to us. So platinum group elements, here we have a little chart, a bar chart, and again, I'll spare you the details, but if you look at ore deposits on Earth, it's the lower red box, and if you look at these iron meteorites, they are as good, if not better, than the best ore deposits we have on planet Earth. So having a large iron meteorite with several hundreds of kilometers, we don't have ore deposits of this size that we're exploiting right now, pure metal ores of hundreds of kilometers dimension. This is not something we have on planet Earth that we're mining right now. So quick note about the differentiation. We need to kind of think about making planets, and how do we do that? Well, some of the diagrams doesn't seem to come up, okay. But there's this idea from Fukai and Suzuki that once we have a lump of chondritic material, then we might heat that up and the metal will segregate. And because metal is very dense, it might actually move towards the center and make a core. And therefore we have a process that concentrates that. So proto-Earth being potentially a chondrite, a lump of chondritic dust, will eventually gravitationally capture more material and will therefore also start to heat up internally from radioactive decay. If we have an atmosphere, we might shield the escape of heat, and eventually the blanketing effect of the atmosphere and the impact energy can yield to iron-rich melts, and they might segregate into the core regions. And if we later break these things up, then we have access to some of the core material, which of course we don't have in our own planet. So to summarize now, the simplest kind of early materials would be represented by the chondrite meteorites, the most common type that we have, and they come mainly from the asteroid belt. Then we have what has been involved in planetary formation. There we have little core materials, iron meteorites. We have pallasites being the transition between core and the silicate outer shell. And then we have achondrites. They are really like our mantle and crust materials. So we have the very primitive ones, and we have the differentiated meteorites and the iron meteorites, the core materials of these small bodies that are now destroyed. They would be the main target. In sense of the Earth, I mean, we have drilled down to about 12 kilometers and we have failed to drill any further. This is the best we can do technically at the moment, but our core starts at about 2,900 kilometers. So reaching the metal in the Earth core is virtually impossible for us, but reaching the metal of a formerly broken up planet or planetesimal, that is actually much more achievable. So this is then the kind of planetary formation concept here, again represented in meteorites, with the iron meteorites being the cores, the mesosiderites being the transition between core and silicate shell, and the stony materials being the outer materials. The mesosiderites are likely impact related, and they would be a mix between metals and silicates and could well be interesting to us as a resource. So very quickly, asteroid summary. We have the parent bodies of stony meteorites, and they're rather low grade, but resources here, nickel, iron, magnesium, but also many other minerals, and importantly, iron and stony iron meteorites. That's the real target materials, I think. They're super metal rich, and there would be a lot of iron, nickel, chromium, cobalt, but also platinum group elements, and copper, gold, molybdenum, etc. And as I said, it's believed that some of them are so full of these metals that we desire that they would be beyond the Earth economy. So if we could get hold of them, if we can develop technology to harvest some of them, this would be a major asset. So future, of course, is out there to be discussed, and I don't know how things will develop. But there's different ideas, and we will discuss this a little bit later in the course, whether we will actually have space stations or whether we can actually attach a space station to one of these asteroids. I really don't know, but people are starting to dream about exploiting them. So thank you for your attention. And this is me holding a very rare meteorite, and I was quite proud, but I couldn't touch it with my bare hands. I had to wear gloves. But here, I'd like to say thank you for your attention. And yeah, if there's a quick question, I would, of course, be very happy to address that. Thank you.